All right, everyone. Thanks for joining us for the last session before, I believe Dude Perfect is right after this, but for now we have Gunche who's going to talk about designing policies using causal AI in SaaS. Take it away.
Thank you, Colby. Hello, everybody. Can you all hear me? Well, that's great. Thank you for joining. By the way, I know it's another ideal timing, but I'm sure you'll enjoy this presentation. My name is Gunje Walton. I'm the product manager overseeing visual statistics and SaaS econometrics. In this demo, I'll be showing you how you can design smarter, more effective policies with causal AI tools in SaaS using Pennsylvania reemployment bonus experiment data. So this study, the Pennsylvania reemployment bonus experiment, is actually a landmark randomized study from late 1980s. So it spans the half of 1988 and the full year of 1989. So there are 6 quarters it spans. The core question there was whether financial incentives could help unemployed workers return to work faster. So UI claimants, unemployment insurance claimants, were assigned to either a control group or one of the bonus offer treatment groups. There were 6 of them, 6 types of bonus schemes. The bonuses ranges from $500 to $1,000 and depended on rapid and sustained reemployment. To be able to obtain the bonus, you have to find the job in a certain time and you have to sustain it for a period of time. So this analysis, my study here, is based on this study. Now, the conclusion of the original experiment was that the effects of the bonus were fairly modest. The bonuses did reduce the UI duration, but the average effects were small, so the program was actually not very cost effective from the UI system's perspective. That is the motivation of my study here. Can we use SaaS AI, causal AI tools to move beyond average causal effects and discover who responds most to the bonus? Then using those insights about the heterogeneity, can we design better, more targeted policies, better than the policy alternatives, better than the existing policy? So let me briefly introduce you to the empirical setup. What I did here is I only focused on the treatment group 4, which was the most generous bonus design. So there were 6 bonus schemes the original study experiment had. I only focused on the treatment 4, the most generous bonus design. The outcome was the log of unemployment duration. And the treatment variable is an indicator variable, an indicator of either you're assigned to a bonus assignment, or a bonus scheme or not. Okay? So the covariates variable, covariates include a set of demographic, household, timing, industry, local labor market condition indicators. Now here, what you see is a high-level view of the workflow for the study. I start with a causal discovery to test whether the variables used in the original study support a plausible causal structure in the data. That structure is represented by a causal graph, or DAG. At the causal graph step, I validate the causal assumptions using the learned DAG as an input. Once I confirm my causal model, I move to causal inference, causal estimation step. So I estimate the effects of bonus treatment and also examine how that effect varies across different UI claimants. Finally, I use those insights for policy design and evaluation and ask whether targeted rules can outperform or perform better than the uniform policy that they're the Pennsylvania reemployment experiment did. Now, in SAS, you can use proc causal discovery for, well, the causal discovery step. You can see the syntax in the code on the left-hand side. So I passed this study. I passed the study variables and asked the procedure to learn the causal structure from the data directly. So one of the outputs that I received from causal discovery is the topological order table. You can see it on the right. So it shows you the initial and final topological order. The initial order is the user entered order, and the final order reflects the ordering that the procedure learns from the data. So the cause appears before the effect in the ordering. So in this example, background variables like manufacturing for example, manufacturing status moves earlier, and then the outcome variable, for example, logged unemployment duration, moves later, which broadly what I expect anyway. So another table that I get from causal discovery, proc causal discovery, is the estimated adjacency matrix. So each row and column represents is a variable. It shows which pairs of vertices or nodes are connected. So an entry of 1 indicates there is an edge from the row variable to the column variable. That is basically from the cause to the effect. And a value of 0 indicates no causal connection between the variables. In the learn statement, if you look at the code, I specify the out path equals option. Basically, this writes the paths of the estimated DAGs as an output data table. So for each variable, the table shows things like parents, children, and directional paths implied by the learn DAG. What I focus here is the last column for the first two variables, the log unemployment duration, my outcome variable, and the TG, the treatment variable, treatment indicator. So the column, the name child at left-hand side path shows the variables that appear upstream in the estimated causal structure. Now I can use the DAG that proc causal discovery outputs as an input to proc causal graph. So at this stage, I want to identify which covariates I should adjust for in order to estimate the causal effects uniquely. Okay? So the causal graph returns valid covariate adjustment sets, meaning that these are the sets of variables that block confounding paths under the assumed DAG. So in our case, we do have at least one adjustment set, valid adjustment set, which means we do have actually a causal model that supports identification of the treatment effect. So we actually have two variables here. The minimal row says that those are the minimum variable set, the set of variables that you should be including in your model to identify the causal effect. And this demo, I'm going to be going with the second row, which is the largest group, largest set. So causal graph also outputs a visualization of the causal graph, the DAG. You can see it here. And it's, our DAG looks like this. I know it's a little bit complicated, but visuals are always nice. Now, once I obtained a valid causal model, I move into estimation using proc deep causal. Now, proc deep causal estimates a range of population and subpopulation average causal effects and performs policy evaluation and policy optimization by using deep neural networks, or DNNs. DNNs overcome several technical difficulties in the big data era, not just the long and wide data, but the huge amounts of discrete and continuous potential covariates, the unknown nonlinear relationships among the covariates, the outcome, and the treatment assignment. In that sense, deep causal is a very powerful tool for causal inference. You can see its syntax on the left. Note that the specification for the hyperparameters for the DNNs are completely optional. If you choose not to specify anything, you go with the default, and that simplifies the syntax even further. So you can see the output of this procedure on the right. Of course, the most familiar estimate is the ATE estimate, average treatment effect. It measures the difference in the average unemployment duration between the claimants who were assigned to the bonus, and those who were not. Okay, so the average difference. In this example, this estimate is about minus 0.084. This is statistically significant. It's small, but it's statistically significant. So given that our outcome variable is a log of unemployment duration, this means that, on average, the cash bonus is estimated to shorten the unemployment duration by roughly 8%. So that's about 1.2 weeks relative to the baseline of 15 weeks in the study. Now, if you noticed, I specified out details equals option in the infer statement on the left. So you can see the part of the output data table on the right that, with my specification, I get this details data, output data. And this is actually very useful table because it provides the treatment effects for each individual observation. So that is one of the most powerful things about PROC-deep causal. And that information I highlighted here in yellow is under the column _AT_. Basically, you can use those individual level estimates to uncover for whom the bonus works better and for whom it works less well. So you can basically look at that distribution and compare subgroups and use them to design smarter, more targeted policies. So that's what I'm going to be doing next. So this is the graph, the graph of the distribution of the individual level bonus effects from the previous output table. The distribution is, first of all, is quite wide, which tells us that there is a substantial variation in how individuals respond to the same incentive. Okay? And it's also bimodal, which suggests that there are distinct response groups in the population. So the next question is, so where is that heterogeneity coming from? What does it look like? To answer that, I look at specific subgroups and compare how their estimated treatment effect distributions differ from the full sample. Now, first group that I'll focus is based on the program entry timing. So this is, I call it group one. The group one includes claimants entering the study from in Q1 through Q4. Okay, so I'm comparing them with the complementary set, which is the claimants entering in Q5 and Q6. So bottom panel is the subgroup, and the top panel is everyone else. So the two the distributions visually are not identical. So entry timing may explain some of the heterogeneity, but the difference is fairly modest still, which suggests timing alone may not be the whole story. Now let's look at a second group. In this subgroup, group two, this subgroup contains early entrants, younger age people, and claimants who also have dependents, one or multiple. So this subgroup appears more responsive to the bonus because its density lies more to the left of the rest of the sample's distribution. So left means negative values, which is obviously preferable, right, in this case. So the heterogeneity becomes more pronounced once we also account for the age and the family status. The third group I look into is considers the early entry, so people who entered in Q1 through Q4, non-manufacturing background, and stronger local market conditions. So relative to that, non-group 3 population or complementary set, this subgroup appears even more responsive to bonus, with a larger estimated reduction in unemployment duration. So these are just, having an idea of what the population looks like, right? Putting everything together on the left, the subgroup bonus effect distributions are overlaid with the full sample in blue, okay? So the dashed line is not zero, by the way. It's the ATE estimate, which is, remember, minus 0.084. And the band was the 95% confidence interval. So group 2 and 3 are clearly shifted toward more negative values, which means stronger bonus effect. Visual investigation is nice so far, but I want to check whether the patterns we saw are also supported by the estimates statistically. So what I do on the right is that what you see on the right table is the ATE, the one we already estimated, and I look at the CATEs, or conditional treatment effects, for each group. So for the CATE is like ATE, however, based on that particular subgroup, are 0.11, minus 0.11, minus 0.21, and minus 0.24. And they are all statistically significant. So quantitatively, these groups, especially group 2 and 3, respond more strongly to bonus than the overall sample. Now, what do I do next? So gaining this kind of insights, now I translate those insights that I obtained from my previous analysis into alternative policy rules. So what you see here, here is starting with TG. TG is my treatment variable, the bonus assignment. So that's my baseline. So I'm comparing against that. So, and then I define a set of benchmark and targeted alternatives. For example, S0 here is the rule that give no one a bonus. S1 give everyone a bonus. These are simple benchmarks. And then S2, for example, here corresponds to group 1 that I considered. S4 corresponds to group 2. S7, group 3. And I also design other ones too here. So let's see how these policies are going to do compared to the base. Now, once I create these alternative policies in my data set and then I can feed that to PROC Deep Causal for policy evaluation, So thanks to the score statement, I don't have to re-estimate because I already saved that estimation data, and now I'm just recalling it with the score statement here. So this table, what you see on the right, reports the expected outcome under each policy. So since the outcome here is log of unemployment duration, obviously smaller values are better. Okay? For example, under the observed policy, what you see is 1.95, which translates roughly 7.03 or 7 weeks of unemployment. And under the policies S6, if you look at that, that corresponds to, S6 is 1.89, which is roughly 6.62 weeks of unemployment. So several alternative policies outperform the observed policy in expected unemployment duration. Now, another useful table that I get from the infer statement is, when I do policy comparison with the infer statement, is the policy comparison table, which you see here. Now, this one shows each alternative policy relative to the observed policy TG. So basically similar information, but a little bit more clear. So negative values are better, right? Negative values are better because it means that the policy yields a lower expected unemployment duration than the observed policy. S1, S2, and S6 all have negative and statistically significant differences relative to TG, my treatment variable. That means that these policies are estimated to outperform to current policy. Now, let's look at a little bit more digestible version of this policy comparison table. So this is the plot of that table. Now the blue dots, I don't know if you can see the color, but the blue dots show the estimated differences from TG, and the horizontal bars show the 95 confidence intervals, and the green vertical line marks the zero difference. So anything that lays on the left of the green line performs better than the observed policy because they imply lower expected unemployment duration. The policy to the right performs worse. Now what you see is again S1, S2, and S6 outperforms the observed policy, so they're on the favorable side. Also, the confidence intervals are also stay below zero. So among them, S1 and S6, S1, remember, was offering everyone a bonus. S6 is targeting early entry non-manufacturing claimants, okay? Show the largest improvements, both around minus 0.06. So S2 is the early entry cohort policy, also improves the current policy. So there are three policies that we can actually use that to beat the existing. So the remaining policies are statistically undistinguishable from the existing policy TG. So some of those other policies look maybe better or worse, but if you look at it, the confidence intervals are actually containing zero, so we can't really say anything better or worse. Now, to conclude, with this example, I showed you how modern causal AI tools in SAS can take us beyond average effects into more targeted policy designs. And more broadly, with this demonstration, I highlighted the full SAS workflow for causal discovery, identification, estimation, heterogeneity analysis, and policy comparison, all in support for smarter policy designs. So better causal insights leads to better policy designs, and that's exactly where SAS can make a difference. Thank you. And please let me know if you have any questions. Thank you.
Yeah, if anyone has a question, you can raise your hand. I'll come around to you. Otherwise, Dude Perfect is happening in about 10 minutes in the ballroom.
May I say one more thing? So this study, actually, I would like to take one more step in this study. Probably I'll write a blog about it. But what is missing in this study is, for example, I'm only concentrating on the log of unemployment duration. And the next step will be, what does that mean monetarily to the government, so that we can have actually a monetary ordering of the policies. Thank you for your attendance. Thank you for coming. Thank you.
Thank you so much.